Hello, so today I'd like to look at Hubert and Schaefer's Magnetic Domains, the Analysis of Magnetic Microstructures. This is a really comprehensive book on magnetic domains. It's a very useful text if you're really interested in these things. So you may or may not remember what a magnetic domain is. There are, inside of a magnet, and there's a picture of them right here, regions where the magnetization, basically the magnetic polarization, points in different directions, like this way and that way. Well, let's say here we've got these two guys, these two domains, and they point in opposite directions, right? This one has its tip going this way, this one has its tip going that way. And if you were to, say, add a magnetic field to this, then, for example, this magnetic domain would shrink, right? And this one would increase in size or something like that. So the sizes and the shapes of the magnetic domains change based on different things. And here you can see lots of different things going on. One of the things is, of course, the field, like I was just talking about. And another one is you can see that there are little things coming in here due to the microstructure, due to the way the crystal, the magnetic crystal, is put together. So these are complicated. These are real world phenomena with real world effects. This is basically what I did for a living for a long time. So let's take a peek at what's inside. All right. We have an introduction about what a domain is, and I just sort of explained that, and a history of the domain concept. So obviously you couldn't actually visualize a domain originally, right? Originally all you did was you had a square, a bit of material, and you could measure a hysteresis loop on it. Let's see if there's a hysteresis loop running around in here real quick. Maybe I should have done one of the hysteresis books. No, I don't see a hysteresis loop readily available, which is very strange for a magnetics book. But that's kind of a bad hysteresis loop. It'd be nice to have there's a hysteresis loop. There's a sort of paradigmatic hysteresis loop. Your magnetization up here and your applied field here. And, you know, he's got different parameters for a perpendicular field as well. So here we're just going to care about perpendicular field is 0, this big square one. So that's a perfect object right there. Doesn't really exist, but basically, you know, in this case you have your magnetic polarization. Let's say we've got our we're going to start up here. We're going to start, well, I can rest it there. So this whole book, let's say, is the magnetic domain. This pen is the direction of its magnetization. This is a perfect single crystal hysteresis loop. What happens with that is that, you know, you have a magnetic polarization of this book, which is pointing this way. And if you keep putting a negative field on it, a field going this other way back towards me, down on your screen, eventually you come to a place here. This is called the coercivity, and that will switch your domain. It'll switch your magnetization like this. And so at that point, you can take off your field and it will remain in this direction. Okay, you've reversed the polarity of the magnet. You've reversed it from north-south to south-north. Then if you come back around here, anywhere in between here and plus HC, this other vertical line, this magnetization is going to stay the same. And then when you get here, it zips on back up, and this flips, and then you can go anywhere between minus HC and infinity, and it stays the same. So that's, of course, a perfect hysteresis loop. Oh, Stoner-Wolfhard theory. Okay. A real hysteresis loop has some curvature to it because of these domains, right? The domains change how things are actually working. So we have these domains. First idea is, just an idea. Then they get some ideas about domain observation, right? So that's going to come in chapter 2. First, there's a little discussion about micromagnetics, which talks about magnetics in ferromagnetic objects. How do you handle modeling these fields from all over the magnet? Because the thing about these domains is, part of the reason why they exist is each little spot in the magnet, each little atom carries some magnetism. And so if you have an atom over here and an atom over here, they're going to each have some sort of magnetism. And you remember that what magnets want, what two individual magnets that aren't connected by anything want to do is flip around. They want to be in opposite directions to minimize their energy. But for a ferromagnet, these atoms are all pointed in the same direction, or mostly all of them. All of them in a domain will remain in the same direction. So there's another thing in there called exchange that we'll probably find in here, so I won't talk about it too much. But micromagnetics is balancing that exchange energy and that demagnetization energy, or another way to put it is the shape energy, the energy from the magnetic fields themselves to create domains. Domain observation techniques. Earliest ones were bitter patterns. Basically, you sprinkle some stuff on a magnet and see what the where the lines are. That'll tell you where the domain walls are, the differences between different spots. And then you get more important things here. Then we get magneto-optical methods like MOC, magneto-optical Kerr effect. Here you're going to shine a light on a magnet. It's going to reflect off, shine a laser generally, reflect off, and then you'll measure the intensity when it comes back. That'll tell you something about, or you measure the polarization, because the magneto-optical Kerr effect will take a polarized elliptical bit of light and rotate it due to the magnetization. And that way you can find out things about the direction of the magnetization using the magneto-optical Kerr effect, which gets you Kerr microscopes and things like that. So let's see if it gives us a block diagram. So here are some patterns. So this is sort of a normal pattern, like this striped pattern. That's kind of normal. That's the sort of thing you normally see. These are pretty wild, right? That's a pretty wild MOC pattern. This is normally what you see, is you see this striped domain pattern. That's kind of a normal thing to happen with certain kinds of microstructures. So you'll have dark bands which are pointed towards me, and the light bands which are pointed away from me. So light is up and dark is down, and I know that because there's a little arrow in each of them right there that you may not be able to see. So this gives us the sort of picture you get from the magneto-optical Kerr effect. And there are some bitter patterns right there. All right, so that's another way to measure them. Transmission electron microscopy. So as long as you have the if you have anything that's magnetically active, you can use it to do that. Transmission electron microscopy, electron reflection and scattering methods. Neither of these I know too much about. Mechanical microscanning techniques. MFM is the one I'm familiar with. In that case, you just take it's a variant of the atomic force microscope. It's a scanning probe microscope of some sort. And so in an AFM, an atomic force microscope, you've got a very narrow, pointy bit at the end of a lever arm. So put that little brush at the end of that, and it's tapping up and down like this, and it changes its frequency if there's something nearby. AFM, atomic force microscopy, you're looking at the topography of a surface. For a really good AFM, you can actually see the individual atoms on the surface of an object, and you see all sorts of images like that these days. For magnetic force microscopy, that little tip there, that little tip, is magnetic. So now what you're looking at is the magnetic force, which is usually dominant. It's much stronger than that interaction force between these different things, as long as you have a magnetic tip and a magnetic domain. Then you have X-ray, neutron, and other methods. You can all sorts of ways to measure these things. Integral methods supporting domain analysis. A lot of these methods will, for example, if this book has two domains, a lot of these methods will show you just a line here, right? So you have to transform into the next integral up, which is, this one down and this one up, right? So you need to do something like that. So that's the way people measure these things. Lots and lots of money if you can do that. Lots of people need that kind of work. Anybody who needs to do things with magnets. If they make money, they need you, right? So remember that. Domains. Domain theory. Now you need a theory of the domains, right? Because this is physics, right? This is the real world. We need an idea about how to figure out what's going on with different domains. How do domains actually form? What do they look like? And basically, what you do is you look at energy. You look at energy. That's the basis of physics, right? After you get out of first year physics, all the physics is really about energy. And so what you look at are the energies of the ferromagnet, energetics of the ferromagnet here. We have that exchange energy, which I was saying previously. That exchange energy is the thing that keeps them aligned. It's like a little spring that keeps these neighboring magnetic moments of atoms pointed in the same direction instead of pointing in opposite directions like they want to. So that's the exchange energy. It's like a little spring. The anisotropy energy. There is a tendency in certain crystals, well, actually in all crystals, for the magnetization to point along certain directions. And that's because the distances between the different atoms are different, right, in different directions. So depending on the direction of the magnetization and the orientation of those, of the magnet, of the, not the magnet, of the atoms in the magnet, there could be a force that's trying to pull your magnetization, pull the directions of these spins of these elementary magnetic moments on these atoms towards a particular direction in your material. So the easiest one is if you have sort of a rectangle. If you have atom here, rather than having a square lattice, for some reason you have we'll call it a rectangular lattice. There are real words for these, but there's no reason to get into that. And one way you could do this, one way we did do this, is you put an atom in the middle. You put an interstitial non-magnetic atom in the middle, and to relieve stress, the atom, this lattice will expand in some directions. And it turns out that for like iron, putting things in the middle, there are certain axes that will expand. Actually, they'll expand randomly unless you do things to make them expand in a particular direction. But you can do that if you put a magnetic field on while you're creating the material. One of the things that will happen is that the stretching will all be in the direction of the magnetic field because it's easier to stretch that way. And when you take the magnetic field off and things try to relax, they can't relax as much because of the interstitial atoms. This only takes a few percentage points. It only takes a few percentage points of that, but it's not that much to get that sort of anisotropy. And there are other reasons for different things. There are order anisotropies. There are all sorts of different ways to do this. There are all sorts of different ways to create an anisotropy. But once you have it, there are easier directions to align in versus harder ones. There's the Zeeman energy, that's the external field. Basically, the direction of the magnetization times the the magnetization times the applied field, and then scaled by the angle. So this is minimum, this is maximum, this is somewhere in between, usually 0. Stray field energy, I'm assuming that's going to be the energy from the little atoms, neighboring atoms all over the place. That's going to come from domain walls, basically, and things like that. It's not really domain wall energy, but shape anisotropy, things like that. There's a whole host of different energies that are based on the orientation of the magnetizations and the domains relative to the actual shape of the material, relative to the actual shape of the domain walls and things like that. Magnetoelastic interactions and magnetostriction, stress causes magnetism. So stress will basically create another anisotropy in your material. So you have to watch out for that. And then you have micromagnetic equations. And I want to look at that. I don't think this is going to be as deep as Brown, but it should still be pretty nasty. There you go. That's your total energy. Exchange, anisotropy, external field, stray field. See, that HT is demagnetization. External stress and magnetostrictive energy. Then you have to take an integral. So it's the kind of fun you'd always wish you'd had. And then you have different ways to look at it. Total free energy, differential equations, and the effective field. Because you have continuity relationships and things like that. You still have lots of little things to worry about. The origin of domains, right? So we have high anisotropy particles, soft magnetic materials, which are sort of ideal, and things like that. Phase theory for domains in large samples, just sort of looking at the domains. I don't want to talk too much about that. Just sort of looking at the domains as different directions rather than trying to look at them in physical space. That's important. Small particle switching. Right? This is basically the single domain switching I'm talking about. If you have an object that's smaller than the size of a domain in that object, that can be true for some objects. Then you get that ideal behavior of the hysteresis loop that I was talking about. So this is sort of where you start with your analysis, is you say, okay, what would happen if everything is perfect? And then you go on and say, well, the world is not perfect. How do we fix that? So in this case, if the size of an object, say a nanoparticle, is smaller than the domain size in the material, then you can simplify your analysis considerably. Domain walls is basically the switching between the two domains. So here we've got some Kerr images, Kerr microscopy, and you can see these little transitions. Those are domain walls. Actually this is a little bit better because you can see how they've inferred the direction of the different domains. Here this gray one is going up, this almost black one is going to the right, this sort of lighter gray one is going down, and this other domain here is going to the left. And this rectangle is sort of the paradigm example of what a domain pattern looks like. This is what you're looking at in a small object usually. I didn't get to 201. So there are some domain wall looking things there. So what we're looking at are these transitions between different domains. And you can see that you have some strange things happening with pinning and stuff like that. So that's well, we've got different kinds of walls as well, based on the energetics. So there are block walls and nail walls, and so on. Okay, what more interesting things? Materials parameters. So when you're dealing with these things, when you're dealing with domains, everything matters. When you're dealing with magnets, just about everything in the material matters. So these are some ways to get some properties. Mechanical measurements. Okay, so these will be finding torque methods and field gradient methods. These are probably for hysteresis loops, I guess. That's what I think. A torque magnetometer, for example. Magnetic measurements. So these are obviously magnetic measurements. So evaluation of magnetization curves, magnetometric methods, stuff like that. Optical magnetometers, inductive measurements. We have different ways to measure these things. Resonance experiments, ferromagnetic resonance is what I did. Basically, what you're doing is usually in like a ferromagnetic resonance, what you want to do is you want to saturate your magnet so that all the different spins are pointed in more or less the same direction, and then you hit it with a small field and look at. Some cases you look at the ringing, in other cases you look at the energy absorption with different fields, and you use that to figure out what the magnetic properties are. There are other ways where you can look at, for example, the domain wall resonances, which is a little bit harder. Magnetostriction measurements, that's different ways to measure the magnetostriction, the amount of magnetization you get, the amount of anisotropy you get from stress. Domain methods, looking at different domain patterns, bubble materials, that tells you how old this is. Stripe domain nucleation and annihilation. We saw stripe domains a little bit earlier, stuff like that. Thermal evaluation of the exchange constant. Well, you need to try to figure out what that exchange constant is. We saw that exchange constant briefly when we were looking at the energetics. We looked at like 138 or something like that. So we have this constant that tells you how strong that spring is. In a way, it tells you how strong that spring is for different, between the two neighboring atoms, basically, two neighboring spins, two neighboring magnetic moments. And that guy, you need to actually find some way to measure. Right. Let's see, where was I? So here you're using thermal evaluation to figure that sort of stuff out. Theoretical guidelines for materials constants. I'm not mixing law for magnetic insulators. I didn't do anything with magnetic insulators. Domain observation and interpretation. Classification of materials and domains, crystals and magnetic symmetry. Reduced materials parameters, size, dimension, and surface orientation. That can be a problem. A lot of times you're just measuring the surface, for example. Bulk high anisotropy uniaxial materials. These are the sorts of things that, if it's really high anisotropy, what that is that's going to be like a magnet that you'd normally think of, like sticking to an refrigerator, because those high anisotropy materials really hold on to their magnetization for a long time, whereas something that you'd use for writing onto a magnetic hard disk the writer, the thing that's acting like a pencil on a magnetic hard disk, has to be able to switch really fast, but that also means that it's not very stable. You don't want it to be stable, you want it to switch really fast. Bulk cubic crystals, so we're just looking at different kinds of crystals. This is sort of your easiest idea here. Well, maybe your second in it. easiest. This bulk high anisotropy uniaxial materials, that's the easiest. But this is still pretty easy to deal with. Uniaxial materials just mean there's one axis of symmetry. Cubic crystals mean you have two or more, well, for a surface, you have multiple directions of symmetry, which means you have multiple easy axes, which gives you stranger rotation curves. Amorphous nanocrystalline ribbons, magnetic films with low anisotropy, that's what I was just talking about. Those are the things used in industry a lot. Films with strong perpendicular anisotropy. Perpendicular anisotropy is something that was used for bubble technology, magnetic bubble technology, which no longer exists. And for writing perpendicularly onto hard drives, which allows you to, get greater density in those things. So very important to have those perpendicular materials. Remember 491 here because it's how many different domain patterns. Also we have whiskers and wires. Those are also fairly easy, to be honest. The relevance of domains. Why do you care? Why do you care? What sort of things come around with bulk soft magnetic materials? Soft means they're easy to switch. Electrical steels, high permalloy alloys, like we'd use for shielding and stuff like that. Amorphous nanocrystalline alloys and spinel ferrites. Those are just different kinds of those things. These are the things you'd use to write onto a hard drive. Permanent magnets. These are the things that you stick to your refrigerator. Nucleation type sintered magnets, pinning type magnets, small particle nanocrystalline magnets. These are also the sort of things that you'd use as pole heads, for example, usually. Think. Recording media is strange because you want something in between these two things, right? You want to be able to switch it when you put a high field on it which is amplified with one of these soft materials, but you don't want to have it switch willy-nilly like it might if it was one of these soft materials, right? You want it to actually hold on to the data for some period of time, so you need something that's sort of a moderate anisotropy. And you had longitudinal recording materials, which had you do exactly what I was saying before. This stripe here, 1. Stripe down here, going down over here, 0. Perpendicular magnetic materials, they're going in the opposite direction. The head of this one's coming here, the tail of this one's going down, coming at you here, so this is oriented upwards, this one's oriented downwards. That gives you, that lets you pack in more material, and it also lets you actually cut out or pack in more bits, and it also lets you cut out bits of the platter that actually cause interference, cause overwrite and intertrack noise sorts of things. Domain propagation devices, those are the bubble memories that I was talking about, and domain shift register devices, and domains and hysteresis, what happens to the hysteresis with the domains. Maybe that has the picture I wanted to put, and that does not have the picture I wanted to show you, although it references some books that I have over there. Alright, so there are some domains in an iron film, bubble memories. Basically they were moving these like little magnetic bubbles around on these different materials, and that's how they wanted to do computing at one point. I don't think it really worked out. Right? It was a little bit too slow. It didn't work fast enough. So, like a lot of nascent technologies, it looks like it's a possibility to fix some problem that's coming up, but that doesn't work very well in the long run. So here's one way to do writing. So this is on a wire, it looks like. That's the sort of thing I used to do there. This looks like something like an MRAM, a magnetic recording material. Magnetic random access memory, a kind of SSD. like flash, but not as cool, or not as applicable. It would have some fairly good uses, right? And it's probably in some ways better than flash, but flash was first. Flash is just semiconductors. Semiconductors have a lot of advantages over magnets as long as you can get the thing to work right, which they can with flash, so it's okay. And here we have some interesting domain patterns. So if you like, so got magnetoresistive sensors. This would be a very bad sensor, I think. See, this is good. This is bad. All right. This is telling you bad things. This is going to give you a lot of funny results. But you can see these are the little domains, right? Here we've got your basically single domain particles, more or less. Single domain on either side. You see there's some transition region up in this area. Over here, we still have a single domain on this side, and then this side, and then we have a lot of funny little domains around here, and over here we've got more domains. These are different directions for the magnetization. So this is a magnetoresistive sensor, thin film devices. Just showing you some domains. Domains are really cool. These domain patterns are always so much fun. This is a very old kind of recording head, showing you the domains in the yoke, which is basically not the part that's actually writing, but it's an important part anyway. That's more or less a shield. There's recording media there. This looks like it's a hammer sort of thing. I'm not sure. Yeah, use the laser to heat this up, these perpendicular dots, so that it's easier to switch the field. That's a fairly common domain pattern here. This is a really common pattern in nature. Once you've seen it, you see it everywhere. This little sort of weird hexagon connected things, a little bit like a maze. Very interesting. I really don't understand why that's so common. So this is a basic perpendicular recording thing. This is your writer here. This is your platter there. And you need to get a current in there so you can switch the direction of your writer. Those are your stripe domains, basically. Well, that's basically, yeah, those are stripe domains. Stripe domains there. That's basically what they use in longitudinal recording. Okay, so this is a very practical book for the physics of domains, and it's a big long one. The first edition, I think this is the second edition. Maybe I'm wrong. I think the earlier one this is the third printing, so maybe it's still the first edition. I thought there was another one that was much thinner, but I may just be remembering a different thing. So anyways, very nice book if you like magnetic domains, and who doesn't like magnetic domains? Take a peek at that if you want. I mean, remember that when you look at something like this, and I think this is one of my favorite textbooks on electricity and magnetism. You know, there's a little bit of a bait and switch. I don't think so much in this one, but you know, you start saying, okay, I'm going to talk to you about. You start talking about magnetism. You say, I'm going to talk to you about your refrigerator magnet. That's what's in this thing, right? This is the kind of thing your refrigerator magnet does. And here they talk about that, and then next thing you know, what are they talking about? They're talking about these currents causing magnetism, and that's absolutely true. It's actually probably a better way, at least if what you're trying to do is create problems, right? But for, you know, I guess I shouldn't say it's for creating problems, because the thing here is that, yes, the domains are important, right? And that's one way to make this magnetic field, but the thing is that the currents mix in with mix in with the electricity, so you can do electricity and magnetism together. So you'll remember this. This is your bar magnet that has a magnetic moment pointing up. That's what this guy is talking about, is what's happening inside those bar magnets. Whereas here is just a loop of wire. Right? Here's so if I could take this paper clip. So if I were to run a current through this paper clip here, this is not a very good circle. If I was to run a current through this paper clip right here, that would give me a magnetic moment. Now, in comparison to this bar magnet, if I had a neodymium magnet or something like that, this would be much, much stronger than anything I could make out of this, right? But with a soft magnetic material, I could use this to switch one of these if it had a small anisotropy, or small, not anisotropy, a small coercivity, a small coercive field, a small place where that hysteresis loop would switch. So I could turn this into a control for something like this. Okay. The analysis for this and this are exactly the same. All right. The analysis for the current loop and for the magnet are exactly the same. But, yeah, maybe not, but pretty close. Once you have a magnetic moment, you can use that magnetic moment. They're all the same, basically, at least at far field, which is not that far. Far field is not really that far for reasonable precision. If you're right up close to the edge of the loop, then it's much different. But if you're far enough away, they act exactly the same. So that bait and switch means you don't actually learn about magnetic domains, the things you wanted to learn about in the first place, the real world of magnetism. All right, and that's what this book gives you, is the real world of magnetism in a lot of detail.